Hello everyone. So in this lecture video, we are going to be starting off on this very treacherous subject of stoichiometry. Stoichiometry are just mathematical calculations involving the unit of mole. Now, what is mole? This is in your exam references as well, and this is just a quarter or a third of that actual table, which is from the website. The mole, there's a relation between moles. So the mole is the chemistry dozen. We all know that in a dozen there are 12 something. So a dozen eggs is 12 eggs. A dozen apples is 12 apples, so on and so forth. In chemistry, the mole is a little bit much more complicated, and the reason why it is much more complicated is because it's signified by this huge number, 6.02 times 10 to the 23. So all you have to think about is you just see this number with 23, in this case actually not 23, but 21 zeros, right? If you eliminate the decimal point, it's going to be 21 zeros following it. So it's a huge number, huge number. So what happens is there's a relation between the number of moles with the molar mass and with the number of particles. So I'll give you an example. So if you look at your table of elements, you should be able to find the element nitrogen here, hydrogen. And if you can see on that actual the periodic table, the weight, the standard atomic weight of hydrogen is 1.007 grams. What that tells you that is in 1.007 grams of hydrogen, there's 1 mole, and in 1 mole, which is equivalent to 1.007 grams of hydrogen, there's actually 6.02 times 10 to the 20 atoms of hydrogen. So as you can see, there's a lot of particles in 1.007 grams of hydrogen. Now, obviously, in the periodic table, all atoms does not have the same weight. So if you compare that with in this case, the atomic mass of beryllium, which is around 9 grams, 9 grams of beryllium will be equal to 1 mole, and 9 grams of beryllium will have 6.02 times 10 to the 23 atoms as well. All right, very important. We're not going to be talking about volume. This volume is going to come into play when we talk about gases. Okay, so again, if we go back to the hydrogen example, 1.007 grams is 1 mole. If I double that, if I have 2.014 grams, well, there's 2 moles. And if I have 2 moles, this number is also doubled, which is going to be, in this case, probably 1.3 times 10 to the 24 atoms of hydrogen. Okay, so that's the relationship. The reason why we talk about moles instead of citing this number all the time is this is a big number, and if we write this all the time, we're gonna get basically carpal tunnel. Okay, and also this is also very important in chemical reactions. In chemical reactions, the collision between gazillions, bazillions, googles of atoms is actually quite likely. And so instead of tracking every single atom out of the googles, and gogol, by the way, is 1 followed by 100 zeros, it's much more better for us to actually define chemical reactions by moles instead of this huge number. Okay, so how do you actually use this mathematical calculus? First of all, you need to be able to find molar masses first. So molar masses is when you go to the table of elements and you actually calculate the masses by adding, multiplying, all of that stuff of given atomic weight. So we're going to go through a couple of examples. So what is the molar mass of carbon dioxide? Carbon dioxide is 1 carbon and 2 oxygens. So what you do is you go to the periodic table. You find that the atomic weight of carbon is 12.01. Since there's only 1 carbon, we multiply that by 1. The mass of oxygen is 16 grams. We multiply that by 2. Why by 2? Because there's 2 oxygens. And we come up with 32 grams. The total molar mass of carbon dioxide is the sum of all of the weights of the atoms combined. Oh, I shouldn't say weight because weight is not a good term, of all the masses of the atoms combined. So in this case, the molar mass of carbon dioxide is 44.01 grams. Right? So molar mass is, in this case, determined by looking at the periodic table. Another example, it's a little bit much more complicated, phosphoric acid, or If you want to talk about it as hydrogen phosphate, fine. Phosphoric acid has 3 hydrogens, 1 phosphorus, and 4 oxygens. Go to the periodic table. Again, multiply the atomic mass of hydrogen times 3. Why? There's 3 hydrogens. 16 times 4. Why? There's 4 oxygens. And phosphorus by 1 because there's only 1 phosphorus. You add all of them together. The sum is the molar mass of phosphoric acid. Okay, very, very important here. So the first thing in order for you to be able to do stoichiometry is you need to be able to determine the molar masses. Now you might be saying, Abner, there's some rounding that you've done there. One of the things is when you use the periodic table is I always like encourage all of you for you to round in the 100th place. So if an atomic mass in your periodic table goes to the 1,000, 10,000, 100,000 place, round to the, in this case, the 100th place, and that should be okay with me. Okay. So just to give you an FYI. Now, how does this turn into, how do you actually utilize, why do we need to do mole masses, and how is this involved in this calculations? Well, let's do some calculations. Before, if we look at molar mass of carbon dioxide, 44.01 grams is equal to 1 mole, which is equal to 6.02 times 10 to the 23 molecules of carbon dioxide. If I double this to 88.02, we know for a fact that 88.02 should be equivalent to 2 moles. And if there's 2 moles, this number also doubles. If I multiply this by 3, that means to say there's going to be 3 moles. This means to say this number is going to get multiplied by 3. If I take a half of this, right? That means to say there's going to be half mole, and that means to say there's only going to be a half of this. So there's a relationship that ripples through all this molar, in this case molar relationships, based on increase, decrease of masses, increase, decrease of particles, increase, decrease of the number of moles. So let's do a couple of mathematical examples. So let's look at this one. So this is not a very straightforward number, right? So how many moles are in 22.8 grams of CO2? So the first thing you do by using this is you identify where you're starting from and where you're ending to. So what is given is 22.8 grams of CO2. Grams is mass. And what is being asked is moles. Which means to say, so then you say, oh, I'm starting here and I'm going towards moles. So it just so happens that it's a one-step problem, mass to moles. And as you can see, the relationship that you need to use is this ratio that says 1 mole given with the molar mass on the bottom. Might as well next. Now here, 22.8. I'm very, very sorry about this little thing. 22.8 grams of CO2 times 1 mole given, 1 mole of carbon dioxide divided by the molar mass of carbon dioxide. What is that? That's 44.01 grams. And this is dimensional analysis all over again, right? So 22.8 grams times 1 divided by 4. And again, if you can see this, the grams of CO2, since this is on top and this is not the denominator, gets cancelled. What unit is left? Moles of carbon dioxide. And as you can see, we already rounded to the correct number of significant figures. 3 significant figures. The answer also has 3 significant figures. So the answer is 0.518 moles of carbon dioxide. So in this case, we went for mass. We identified where we're starting from and where we're ending. So from here to here, we use this relationship, which is the 1 mole over the molar mass. And the molar mass is calculated by going to the periodic table. Going the opposite way, how many grams are in 2.2 moles of carbon dioxide? So we're going from moles. So this time, folks, we're going from moles to mass. Here's the deal. If you're going from moles to mass, if you look at the arrow, we are going against the arrow. When we go against the arrow, the ratio that is displayed underneath gets reversed. So instead of writing 1 mole given over molar mass given, what we're going to do is we're going to flip this ratio, and now the molar mass goes on top and the 1 mole is on the bottom. So again, anytime you start and you end and you go against an arrow in this table, you flip the ratio underneath. So all you think about is you flip the ratio underneath. So now it's 44.01 grams of carbon dioxide over 1 mole. Do the math. And again, the answer is 97 grams of CO2. Now, why do I need two significant figures? There's only two significant figures here. So we always base upon our answer based on what's given to us. Okay. So again, before in the previous in the first example, we went from grams to moles. Grams starts here, moles here. We used the ratio as indicated. The second problem went from moles to mass. We are going against the arrow. We flip the ratio underneath. And where do we find this ratio? The ratio is by calculating the molar mass by using the periodic table. Okay. A little bit much more complicated problem. How many particles are in 20 grams of carbon dioxide? So in this case, particles are here. And we're starting here in mass. So we're going from mass to moles. We're not done yet at that point. And then we're going to go from moles to particles. So this is going to be a two-step problem. Mass to moles. We use this ratio. Moles to particles. We are going against the arrow. So this ratio gets flipped. And if I write everything out, again, you guys can read this. 20 grams, the given, times this ratio. Written the way it is. 1 mole on top, molar mass on the bottom. Then, as you can see, I'm at moles now. I'm going to go to particles. I flip this ratio here because I am going against the arrow. 6.02 times 10 to the 23 molecules of CO2 divided by 1 mole of CO2. Okay, so this is very, very important now. And then we just do the math, folks. And what happens is 20 times 1 divided by 44.01 times 6.02 times 10 to the 23 divided by 1. The answer is 2.74 times 10 to the 23 molecules of carbon dioxide. Okay, so that is actually where that stands. Again, why do we need three significant figures? The number that's given has three significant figures, so we need to end with three significant figures. So there's a wrinkle in all of these things. And if we cancel unit, by the way, grams cancel that grams, moles cancel that moles, and we're end with molecules, which is the question says particles. So particles is a generic term. There are certain rules about particles. In an ionic compound, so if I give you sodium chloride is obviously an ionic compound. The name for particles in an ionic compound are formula units. So if this was NaCl, the answer would be not molecules but formula units of sodium chloride. If I gave you sodium ion, Na plus or Cl minus or anything that has a charge, whether it's positive or negative, that is called ions, and we call them ions. So if I ask how many particles are in Na plus or H2PO4 minus, the answer is going to be ions of Na plus or ions of H2PO4 minus. If I give you an element means to say it's straight from the periodic table. If this question was, let's just say boron, no subscript, it's not connected to anything, the answer would not be molecules, it would be atoms. Okay, so again, if this was a covalent compound, molecules are fine. If this was an ionic compound, you need to use formula units for particles. If this was an ion, Na plus, Cl minus, anything that has a positive or negative charge, we use ions. If this was just an element by itself, like boron, Na, no charge, Si, no charge, we use atoms. Okay, again, please make sure that you're familiar in how to use this. Again, you identify where you're starting and you find where you're ending. And again, if you go with the arrow, you use the ratio as written. If you go against an arrow, you flip the ratio as given.